Correct.
So we will wait. 54 students have joined so far. This class.
Level.
Is it visible to everyone? Hello.
Yes, sir.
Yes, sir. Okay. So let me start with what we have started looking at in the last class. Okay, so in the last class we started looking at under dam system, and uh, after that we said that we are going to look at some examples of uh, over dam system, critically dammed system, and under dam system, isn't it? So again, towards the end in the last class we started looking at the examples of over dam system, and we said in a over dam system there are you can see that if we are taking the tank system, there are two possibilities. The first one is, the first case is a non-interacting system. So in a non-interacting system, you can see that uh, the dynamics of the first tank is impacting the dynamics of the second tank, but the dynamics of the second tank is not impacting the first tank. So you can see that the output from this not there. Dynamics of the first second tank is also is if let's say F1 that uh, uh, if you look at the on H1 H1 interacting system, but unlike that tank, but the first okay. Uh, the second case, one when we look at the but the stir tank. If you look at differential equation, I'll show the how first order transfer. But if I look at y is not constant, order differential. dt by dt given as will come into the picture.
Yes, sir.
Yes.
Go back. Okay. This is there are two capacitors. Tau P1 so this is the this Y1, which is the output of the first capacity, is then given. So with respect to that, the expression will be tau P2 dy2 by dt plus Y2, and that should be equals to Kp2 Y1t. So you can see that this Y1t is the input to the second system, whereas the output is Y2t. So this example can be represented in the form of block diagram as shown here. You can see that F1 is given as is Y2 here. Between Y1 and Y2, the transfer function is G2. In this manner, we can have n such first order capacities in series which can be arranged in a non-interacting manner. And in such cases, we will have a nth order system. Okay. Is there any question? Hello? So you can see that if we are having two capacities in series if these are arranged in a non-interacting manner, we get the expression for G1 and G2 as Kp1 by tau P1 S plus 1. That is the expression for G1. Similarly, for G2, we get Kp2 divided by tau P2 S plus 1. And if we are interested in finding out how Y2 is related with this F1, in that case, we will get a overall transfer function, which is nothing but G1 multiplied by G2. So in this case, overall transfer function will be given by Y2S divided by F1S, and that is nothing but this first transfer function multiplied by second transfer function. So you can see that the first transfer function is nothing but what? First transfer function is nothing but Y1S divided by F1S, and into second transfer function, which is nothing but Y2S by Y1S. This Y1S and this Y1S will get cancelled out, and ultimately we will get Y2S by F1S, isn't it? So with this, we can. Hello? Is my slides visible?
Yes, sir.
Yes, sir.
So in this case, you can see that we will get the overall transfer function G naught S will be given by Kp1 divided by tau P1 S plus 1 into Kp2 divided by tau P2 S plus 1. So clearly here the denominator is second order in terms of S. So clearly the obtained system is second order. And also we can find out what are the roots of the denominator here. So roots of the denominator I'm going to get minus 1 by tau p1 and minus 1 by tau p2. And both these roots are real and distinct. And therefore, whenever we have multiple capacities arranged in a non-interacting manner, we are bound to get real and distinct root, and therefore the system will be over damped, or at max it can be a critically damped, isn't it? So critical damped system we will get only when the damping factor is 1. So in this case you can see that if I rearrange this, I can get the damping factor zeta equals to 1 only and only when this tau p1 is exactly same as tau p2. If this tau p1 is exactly same as tau p2, in that case we will get multiple roots here. We will get two roots, and both the roots are nothing but what? Minus 1 by tau p1, isn't it? Or tau p2, since tau p1 is same as tau p2, isn't it? So whenever the tau p1 is same as tau p2, we are likely to get a critically damped system. And if I look at this tau p1 is actually what? Tau p1 in this case, for this particular case, the tau p1 is nothing but a1 r1. Similarly, tau p2 will be what? A2 r2, isn't it? Let's say if we take this resistance as same, in that case, the critically damped system I can get only and only if both the tanks are of equal size. Is it clear to everyone?
Yes.
So what we can conclude here is whenever we have multiple capacities in series, then we can get only overdamped system. And if the time constant of the different capacities are same, in that case we will get critically damped. But no way we can get underdamped system in this case, isn't it? We can get overdamped, or at max we can get critically damped. Underdamped system is not possible whenever we have multiple capacities in series. Is it clear to everyone?
Yes.
So up to this we have already seen in the last class. Okay. Now let's look at the given system. We can have, this is the transfer function, isn't it? This is the transfer function we have obtained, overall transfer function. Now let's assume that the input to this particular system is a step input of magnitude unity. So that means what? This f1s is nothing but what? 1 by s. So I can put this f1s equals to 1 by s, and I can invert this particular equation in a time domain in order to obtain the y2t. So with inversion, we are going to get y2t, and y2t will be obtained as what? Y2t will come out to be kp dash. Remember, in this case, kp1 into kp2, that is given as kp dash. So we will take this kp dash outside here into, in the bracket, 1 plus tau p1 e raised to the power minus t by tau p1 minus tau p2 e raised to the power minus t by tau p2 divided by tau p2 minus tau p1. So this is a generalized expression which we have already derived earlier, isn't it? So the same expression we are expected to get in this case. Okay. Now we can solve this particular problem easily in this case, primarily because the transfer function had only two capacities, isn't it? So we had only the denominator with order 2, isn't it? But let's say if you are having n capacities in series, in that case this denominator will be nth order polynomial. In such cases, obtaining the solution is not easy. It is going to be cumbersome. It is going to be slightly more complex than this. So there is something called as, Cohen-Kuhn controller tuning that we will see. At that time we will see, whenever we have such a complicated transfer function, how we can deal with such complicated transfer function, that we can see as we go ahead. Okay, but for a timing, let's concentrate only on second order system. Now this particular discussion, let's look at in the context of two tank system, isn't it? So in this case, this is the non-interacting two tank system. Here you can see that the inlet to the first tank is Fi, isn't it? Then outlet, if I'm looking at the tank 1, the outlet is F1. This F1 is given as an input to the second tank, and with respect to that, the outlet is F2. I am interested in finding out how this height in the tank 2 is varying when there is a change in the Fi values. Let's say if there is a disturbance in Fi, in that case, how this H2 is going to respond to change in Fi, that is what I am trying to look at. Okay. So in this case, what will be given? The first transfer function in this case will be what? If I look at this particular case, the first transfer function will be nothing but how this H1 is related to F1. That is the first transfer function, isn't it? Remember, in this case, the differential equation which we are going to get is what? A dH1 by dt will be equals to Fi minus F1, isn't it? And F1, I can take it as H1 by R, isn't it? If I rearrange this, I'm going to get A1 R1 dH1 by dt plus H1, and that should be equals to R into Fi, isn't it? That is what I'm expected to get. Do you all agree with me? Yes or no?
Yes, sir.
So you can see that in this case, if I apply the Laplace transform and obtain how this H1 is related to Fi, I am going to get Kp divided by tau p1 s plus 1, where Kp is nothing but what? Kp is nothing but R1, whereas tau p1 will be nothing but A1 R1. Do you all agree with me? Correct? Yes or no?
Yes, sir.
Yes.
Similarly, for the second tank, we are going to get the transfer function. We are going to get Kp2 divided by tau p2 s plus 1, where Kp2 will be nothing but what? R2, and tau p2 will be. Please mute yourself if you are not having any question. And tau p2 will be A2 R2, isn't it? Correct. So same thing we have written here. So you can see that G1 will be H1s divided by Fi dash s. That will be nothing but Kp1 divided by tau p1 s plus 1. Similarly, G2s will be H2 s divided by F1s, and that is given as Kp2 divided by tau p2 s plus 1. Here Kp1 is nothing but R1, and here Kp2 is nothing but R2. Similarly, tau p1 in this case is going to be A1 R1, and tau p2 will be A2 R2. This is the same thing which we have, directly writing from the derivation we have seen earlier. Do you all agree with me?
Yes, sir.
Yes, sir.
Now I am interested in G naught S. I am interested in overall transfer function. Now overall transfer function is given by what? In this case, how this H2S related with FIS, that is what the overall transfer function is. Correct? Yes or no? How this H2S is related to FIS, that is what the overall transfer function is, isn't it? Now, if I multiply G1 to G2, I am not going to get that. Why? Because here you can see that the numerator is H2S, denominator is F1S. Here the numerator is H1S and denominator is FIS. You can see that this H1S should be cancelled out, isn't it? Then and then only I will get H2S by F1S, H2S by FIS. Otherwise not. So we need one more relation here. How this F1S is related to H1S, that is what is required. So F1 is given by what? F1, the outlet flow rate from the first tank is nothing but what? The height of the tank divided by resistance, isn't it? Height of the liquid in the tank divided by resistance. So F1 dash will be given by H1 dash divided by R1, isn't it? I can apply the Laplace transform. I'm going to get F1S divided by H1S, that will be 1 by R1, isn't it? Now I can multiply this additional term here, and if I multiply G1, G2, then this F1S will get cancelled out with this F1S, and this H1S will get cancelled out with this H1S, and finally I'm going to get H2S divided by F1S. So there is a small difference. There is a small extension with respect to what we have done earlier here. These are the small details which we usually miss if you don't derive it ourselves, isn't it? So don't just rely on the notes, okay? Otherwise you will be lost here. So you can see that this additional term we have to multiply in G1 and G2, then and then only this H1S and this F1S get cancelled out, and ultimately we get H2S divided by FIS. So that is what we have done. See, H2S by FIS is nothing but what? H1S by FIS, that is nothing but this G1. This F1S divided by H1S, this is nothing but this additional term I am looking at, multiplied by this G2S, which is nothing but H2S divided by F1S. And now you can see this F1S will get cancelled out with this F1S. This H1S will get cancelled out this H1S. And finally, I'm going to get H2S divided by Fi dash S. So this additional
Excuse me, sir.
term, this
Sir, just to cancel, we can't multiply any term, na? So we have to multiply or divide. So we don't have an extra term.
so that is what we are doing here. You can see we are not multiplying it arbitrarily. Remember, in this case, my outlet. Uh, uh, just a minute. Maybe I'll explain. Just a minute. We are not doing it arbitrarily. There is a reason. Okay. Let me put a writing pad. Then probably I will explain. Just a minute. Give me a minute. So see, in this case, if I look at this earlier derivation here we got G naught is nothing but what? G1 into G2. This is what we have obtained, isn't it? Now let's look at this case. In this case, if I multiply G1 into G2, if I do, what I'm going to get? I'm going to get this H1 dash S divided by Fi dash S into H2, sorry, H2 dash S divided by F1 dash S. This is what I'm going to get. Correct. But I am not interested in getting this. I am interested in getting what? I am interested in getting how this H2 dash S is related to how this H2 dash S related to Fi dash S. This is what I'm interested in. I can get this. This is nothing but the overall transfer function I'm looking at. Now this I can get by multiplying this additional multiplication. If I multiply here, F1 dash S by H1 dash S, then I can get this. Do you all agree with me or not?
Yes,
Isn't
sir.
it? So this small change is coming primarily because why? This small change is coming because the inlet to the second system, if you go back and see, if I look at this particular case, here you can see that the outlet is what? Outlet here, outlet from the first system is Y1, correct? And this Y1 is given as a input to the second system, isn't it? Now, if you look at the two tank system, what is the outlet here? Don't look at the outlet in terms of flow. Look at the outlet in terms of the equations. So outlet here is, the output variable here is H1. Then input is Fi, isn't it? Correct? Do you all agree?
Yes, sir.
But this H1 we are not giving as a input to the second system. We are giving a F1 as a input to the second system. And that is why this additional multiplication term we have to add there. Is it clear to everyone now? Isn't it? Unlike this, here, see, Y1 is the output and the same Y1 is given as an input to the second system. Unlike this, in this particular case, this H1 is the output, but H1 is not given as an input to the second tank. Instead of H1, we have given F1 as a input to the second tank. Of course, I can convert this H1 to F1 because F1 will be nothing but what? F1 will be nothing but what? H1 by R1, isn't it? So I can convert F1 in terms of H1. But the output from the first tank, which is H1, is not directly given as an input to the second tank. And that is why this additional multiplication factor we need to multiply here into G1 and G2 in order to make the multiplication compatible. Do you all agree with me?
Yes, sir.
Is it clear? These are the small changes which usually we miss out. Okay. So now with this multiplication, what we are going to get? If I multiply this, you can see that. So see, this F1 by H1 is nothing but what? F1 dash S by H1 dash S, that is nothing but 1 by R1, and R1 is what? KP1. So this term is nothing but 1 by KP1. So now multiply here. So this is the first transfer function. This is the second transfer function, and this additional term which we are multiplying here, that is nothing but 1 by kp1. So you can see that this kp1 will get cancelled out with this kp1, and ultimately what we are going to get is kp2 divided by tau p1s plus 1 into tau p2s plus 1. So here you can see that instead of having kp dash, here the numerator is nothing but kp2, which is nothing but r2. Do you all agree?
Yes, sir.
Isn't it? So here the process gain is just kp2, which is nothing but r2. Again, inverting the same expression we will get, except this kp dash, we will get kp2. That is what we are going to get. Rest all are exactly same as the earlier equation. Is it clear to everyone? If we invert back this particular transfer function to a time domain for a the FIS equals to 1 by S, that is nothing but, if we give a step input of magnitude unity in FIS, then we are going to get H2 dash T is given as KP2 in the bracket 1 plus tau P1 e raised to the power minus T by tau P1 minus tau P2 e raised to the power minus T by tau P2 divided by tau P2 minus tau P1. Now, let me erase this writing. Discard. Let us discard. Is it visible to everyone? Slides are visible?
Yes.
Okay. So now let's look at, so see, so far we were only concentrating on non-interacting system. Let's concentrate on interacting system. So interacting system, again, we can derive the expression similar to what we have done so far. So this is the interacting system. Here, let's write down the model equation. So for the first tank, we can write down the model equation as A1 dH1 by dt, that is given as Fi minus F1. And similarly, for the second tank, we can write down the expression as A2 dH2 by dt equals to F1 minus F2, isn't it? Now, in this case, the important point to note down here is, if we assume that the flow rate here, F1, is linearly proportional to the hydrostatic head. So hydrostatic head in this case will be what? H1 minus H2, isn't it? So the flow rate here will dependent on H1 and H2. So we can take the flow rate F1 as H1 minus H2 divided by R1. Do you all agree? Is it clear to everyone?
Yes, sir.
Similarly, the outlet flow rate here will be dependent on the hydrostatic head in the second tank. So that is given as H2 divided by R2. Now let's put this F1 and F2 in this equation and simplify. So if we put this F1 in the first equation, what we get, and if you multiply this entire equation by R1, what we get is A1 R1 dH1 by dt plus H1 minus H2. So what we have done here is this F1 we have put as H1 minus H2 divided by R1, and then we have multiplied this entire equation by R1. So this R1 comes here. So that becomes R1 A1 dH1 by dt. And this, instead of this F1, we will have H1 minus H2, that we can take it on the left hand side, isn't it? So that becomes plus H1 minus H2, and this Fi will be multiplied to R2. So that is what we are, Fi will be multiplied to R1. So that is what we are getting. A1 R1 dH1 by dt, H1 minus H2 R1 F1. Now this equation we can again write down at steady state. So at steady state, this term becomes 0. This becomes H1s minus H2s, and that should be equals to R1 FIS, isn't it? Now this steady state equation, if we subtract from this original equation, we get the equation in a deviation form. So we get A1 R1 dH1 dash by dt plus H1 dash minus H2 dash, and that is equals to R1 Fi dash. Okay. Similarly, we can do the similar thing for the second equation. We can put this F1 as H1 minus H2 by R1, and we can put this F2 as H2 divided by R2. And we can multiply this entire equation by R2. So we will get here R2 into A2 dH2 by dt. And remember, in this case, F1 is nothing but what? H1 minus H2 by R1. And if I multiply R2, that becomes this H1 minus H2 is there. So H1 multiplied by R2 by R1. Similarly, minus H2 divided by R1, R2 by R1, isn't it? And this H2 and this H2 here, both we can take as common. So that becomes 1 plus R2 by R1 into H2. This entire term we can take it on the left hand side here. And that's why instead of minus sign, we will get a plus sign here. And this F1 will be given by what? The term here remaining will be H1 R2 by R1, isn't it? So that R2 by R1 into H1, that again we take it on the left hand side. So that becomes minus R2 by R1 H1, and that is, this entire term becomes equals to 0 here. If you take both these F1 and F2 on the left hand side. Now we can write this equation again at a steady state. So at steady state, what we get is this term becomes 0. This term becomes 1 plus R2 by R1 H2s minus R2 by R1 H1s, and we can subtract this from the original equation. We get an equation in a deviation form, which is nothing but A2 R2 dH2 dash by dt plus 1 plus R2 by R1 H2 dash minus R2 by R1 H1 dash. Okay, now these are the two equations. These are the two equations which we have obtained here. These are the two equations we have obtained. Now we can apply the Laplace transform to both the equations. Let's apply the Laplace transform to this equation. What we are going to get? A1 R1, and the Laplace transform of the derivative becomes S into H1s. And that H1s, if I take a common with this H1s, we will get A1 R1s plus 1, and the common will be H1 dash s. And the Laplace transform of this second term is going to be minus H2 dash s, and the right hand side is going to be R1 Fi dash s. Similarly, this equation also we can apply the Laplace transform. Let's take this second term first. So that becomes R2 by R1 H1 dash s. Then this particular term will have A2 R2 into S into H2 dash s, isn't it? And this H2 dash s is also here, isn't it? We can take this H2 dash s common. So we get A2 R2 s plus this 1 plus R2 divided by R1, and this H2 dash s as a common here. Now these are the two equations which we have. These are the two equations we have obtained in a Laplace domain. I can obtain from this particular equation. I can obtain H2s. This H2s I can calculate. So H2s will be given by what? Plus R2 by R1 H1s divided by this entire bracket. That is going to be H2s. And that H2s I can put in this particular equation. So you can see that this entire equation becomes in terms of H1s and Fi dash s. And if I rearrange the term, I can obtain H1 dash s divided by Fi dash s, and that comes out to be tau p2 R1s plus R1 plus R2 divided by, denominator comes out to be tau p1 tau p2 s square plus tau p1 plus tau p2 plus A1 R2 s plus 1. Similarly, we can obtain H1s from this particular equation. We can obtain H1s from this particular equation here, isn't it? And we can we can put that H1s here in this particular equation, and then we can find out how H2 dash S is related to Fi dash S. So if we do that, what we get is H2 dash S divided by Fi dash S. That comes out to be R2 divided by tau P1 tau P2 S square plus tau P1 plus tau P2 plus A1 R2 S plus 1. Now, if we compare this particular equation with a similar equation which we have obtained for a non-interacting tank. Remember, for a non-interacting tank, this is what the expression we have obtained, isn't it? For a non-interacting tank, if you look at, this is the expression we have obtained, isn't it? So Kp2 divided by tau P1 into tau P2 S square plus tau P1 plus tau P2 S plus 1, isn't it? That is what we are going to get. So if I compare this particular expression, maybe I can go back here. If we compare this particular equation, you can see I can write down. So see, in terms of the expansion, what I'm going to get for a non-interacting system. For a non-interacting system, I am going to get H2 dash S divided by Fi dash S, and that will be given by Kp2 divided by tau P1 tau P2 S square plus tau P1 plus tau P2 and multiplied by S plus 1. This is what the term I'm going to get. Do you all agree with me or not? Correct?
Yes, sir.
And now this particular term which we have obtained for non-interacting system, let's compare that with the similar expression which we have obtained for interacting system. For an interacting system, we have obtained a similar expression which is nothing but H2 dash S divided by Fi dash S. You can see that this expression and the other expression is same, except that this particular additional term is coming in the interacting system. In interacting system, A1 R2, this is the additional term we are getting. And this additional term A1 R2 is referred as interacting factor. This is referred as the interacting factor. Now this interacting factor term A1 R2 is a very interesting term. Why I am saying? Because higher the value of A1 R2, you will see that the value of the zeta increases with this. So as the value of A1 R2 increases, the zeta value, which is nothing but the damping factor, is going to increase. And therefore, as more the interacting factor is there, my system is going to become more and more overdamped. I'm going to get the system is going to become more and more overdamped as this interacting factor A1 R2 increases. Okay. And as the value of zeta increases and the system becomes more and more overdamped, what will be the response? Response is going to become more and more sluggish and delayed. Do you agree with me or not?
Yes, sir.
So this is what we see here. Now let's look at, okay. So why I am saying that the damping factor is going to increase here? See, we are ultimately interested in finding out the roots of the denominator. This is the denominator. Remember, the fastest non-oscillatory behavior, the fastest non-oscillatory response we are going to get when my system is critically damped. Do you all agree with me or not? I can go back and show you. See, the fastest non-oscillatory response we get when my system is critically damped. That means zeta is equals to 1. And when my roots of the denominators are same, in that case we get the critically damped system, isn't it? Now you can see here, let's find out the roots of this denominator. So what will be the roots of this denominator? This is the quadratic equation. So roots will be minus b. So minus of this particular term plus or minus under root square of this particular term into 4 into this term into 1, isn't it? So that is what we have written. Let's say if you find out two roots here, let's say these two roots are P1 and P2, that will be given by minus tau P1, tau P2, A1, R2. So this is nothing but minus of this particular term plus or minus under root square of this particular term minus 4 into tau P1 and tau P2 and divided by 2 tau P1, tau P2. Is it clear to everyone how we are writing this equation? We are trying to find out the roots of the quadratic equation. Remember, in this case, this denominator is quadratic in nature. We are trying to find out the roots of this quadratic equation, isn't it? So roots will be given by this particular expression. And now this expression is very, very interesting. Why I am saying that this expression is very, very interesting, because you see the term which is there in this under root. The term which is there in the under root is tau P1 plus tau P2 plus A1 R2 whole square minus 4 tau P1 tau P2. And this term which is there in the under root, this term is going to be always positive in this case. It is going to be always positive. It's not going to be 0. It is not going to be negative. It is always going to be positive, isn't it? Remember, if I remove this particular term and square this term, then and then only I am going to get this entire term equals to 0. Otherwise not. Do you agree with me or not? Yes or no? So this particular term is always going to be positive because tau P1 is a positive number. Tau P2 is also a positive number. A1 is the area which cannot be negative. R2 is the resistance which also cannot be negative. So you can see that this particular term is going to be always positive. And if I'm having this entire term always positive, what type of roots I'm going to get? This term is positive. That means my roots are going to be always real. Do you all agree with me or not?
Yes, sir.
My roots are going to be always real. I am not going to get imaginary roots. Also, this term is not going to become 0. Remember, whenever this term becomes 0, then and then only I get both my roots P1 and P2 equal. Otherwise, I don't get the equal root. I get the equal root only and only if this particular term becomes 0. And this term is not becoming 0. This is always positive. So I am not going to get critically damped system. Also, I am not going to get under damped system. And I'm only going to get, in this case, is a over damped system. And this is commonly asked question in the interview. Whenever we have a interacting tank, which system we are going to get? Is it going to be over damped, critically damped, under damped? The answer is whenever we are having the interacting capacity, we always get over damped system. It is not possible to get critically damped. It is not possible to get under damped. The only possibility in this case is a over damped. Remember, in an interacting tank, which we have seen earlier, in an interacting tank, interacting tank, we can get critically damped here. We can get a critically damped here. We will not be able to get under damped here, but critically damped is possible when my tau P1 is equals to tau P2. Then I can get a critically damped when I'm having a non-interacting. But instead of non-interacting, let's say if I'm having interacting capacities, then even the critically damped option is out of the question. Only the over damped system we are going to get. Is it clear to everyone? Yes, no?
Yes.
Okay. So when this term is, let's say, positive, always positive, my roots are real and distinct, isn't it? Now let's say I wanted to represent this interacting system. Let's look at this interacting system in the in term similar to the non-interacting system. Let's say if I represent this entire system with the equations of non-interacting system, how I can represent in terms of the non-interacting system? I can use this P1 and P2 as the apparent time constant, isn't it? I can relate this P1 and P2 with the apparent time constant. Maybe I can represent the time constant tau 1 as -1 by P1 and the another time constant as -1 by P2, isn't it? And then my expression becomes h2 dash s by fi dash s becomes r2 divided by tau p1 tau p2, and the denominator I am representing as s minus p1 and s minus p2. And you can see that if I rearrange the term, I get tau 1 tau 2 r2 divided by tau p1 tau p2, and the denominator becomes tau 1 s plus 1 tau 2 s plus 1. So now you can see that the interacting system I have represented in a similar form as that of non-interacting, isn't it? So this expression where this tau 1 and tau 2 are the apparent time constant. They are not the actual time constant. Remember, in this case, the actual time constants are what? Tau p1 and tau p2. I am saying tau 1 and tau 2 are the apparent time constant. This apparent time constant we have taken here in order to convert this entire expression of the interacting system to a non-interacting system, isn't it? I am representing this interacting system mathematically as if it is a non-interacting system, isn't it? If I am doing that, then this tau 1 and tau 2 becomes the apparent time constant, isn't it? So apparent time constant tau 1 and tau 2. Now let's look at the physical significance of this tau 1 and tau 2 here. So tau 1 and tau 2, if I take the ratio of tau 1 and tau 2, that will be nothing but what? That will be P2 divided by P1. That will be just P2 divided by P1. So P1 and P2 are given here, isn't it? So if I take the ratio of P2 by P1, what I'm going to get? See, P2 will be, in this case, P2 will be, let's say if I take positive root as a P2 and negative this positive term here, with this positive term I am taking P2 and the negative term I am taking, let's say, P1. In that case, P2 divided by P1, you can see that only the positive term coming in the numerator and the negative term coming here in the denominator. Now the interesting fact to note down here is, even though let's say both the tanks are same, remember, here we have assumed that when we had the non-interacting capacities, we have assumed that when two tanks are same, in that case, their time constants are going to be same, and I'm going to get the critically damped system. Now let's assume the two tanks are arranged in a interacting manner and their size is same and their time constants are also same. Now what will happen to this ratio? Let's say the time constant are same. In that case, it is going to become 2 tau a1 r1 plus under root a1 r2 square, isn't it? Plus 4 tau a1 r2, and this entire term is subtracted here. You can see that both tau 1 and tau 2 are positive. The only difference here is the tau 1 will be higher than tau 2. So you can see that even though tau p1 and tau p2 are same, even though tau p1 and tau p2, which are nothing but the actual time constant of both the tanks, are same, but their apparent time constants are different. That means one apparent time constant will be higher and another apparent time constant is going to be lower because of this interacting factor A1R2. So higher is the interacting factor, one time constant will increase, whereas the another apparent time constant is going to decrease, and clearly the higher value of the time constant will dominate, will give you the rate limiting step, isn't it? Remember, the time constant basically gives you the speed of response, isn't it? So in this case, the higher value of tau is going to give you the limiting step, isn't it? So clearly you can see that whenever I am having the interacting system, since the apparent time constant of one of the tank is going to increase above its actual time constant, my system response is going to become sluggish. Can you see physically why the system response is going to become sluggish and delayed in this case? Is it clear or not clear? Slightly more, mathematical here, but it's an interesting concept. So what we are trying to say here is, since one of the apparent time constant is going to increase beyond its actual time constant, which is nothing but tau p1, and another time constant, which is nothing but tau 2, which is going to become lower than the actual time constant. But since the higher value of the time constant will be the rate limiting, because the higher is the time constant, sluggish is the response, isn't it? So this tau 1 is going to dominate is going to give you the rate limiting step, and because of that, the overall response of the two tank system when these are connected in a interacting manner is going to response is going to become slower compared to when the tanks are arranged in a non-interacting manner. So you can see that the higher is the interacting factor A1 R2, slower is going to be the response, isn't it? Is it clear? No. Clear or not clear, or this is slightly more complicated? Hello?
Clear, sir, clear.
Okay. All right. So far we were looking at second order system when we have the multiple capacities in series. Remember I said we can get a second order system by three ways. First way is when we are having multiple capacities in series, then we get a second or higher order system. The second case is when we are having inherently second order system. So inherently second order system we get whenever there is a inertia associated with the system. So you can see that whenever the system has a inertia, we can represent the force balance. So force balance will be given by what? Balance of the forces on the system, and that should be equals to mass of the system into acceleration, isn't it? And this acceleration is nothing but what? Change in the velocity, isn't it? Acceleration is nothing but dv by dt, and this velocity is nothing but ds by dt, where s is nothing but spatial displacement. So in terms of spatial displacement, if I represent this entire equation, I get a second order differential equation, and therefore we are likely to get inherently second order system whenever we are having the inertia associated with the system. Is it clear to everyone conceptually? Hello? Is
Sir,
it
I
clear?
want to ask one thing.
Please ask.
Sir, does the modified time constant still has the properties of the time constant which was used in first order system?
So actually, okay. So in this case, this modified time constant, apparent time constant, these are the actual time constant which will be shown by the system. Even though tau p1 and tau p2 are coming from a1 r1 and a2 r2, isn't it? But the actual apparent time constant will be tau 1 and tau 2. Correct. So your system is going to behave with respect to this tau 1 and tau 2, not this tau p1 and tau p2. Is it clear?
Okay, sir. Yes.
So clearly, even though this tau p1 and tau p2 are same, and if I arrange the two tanks in a non-interacting manner, in that case, I'm going to get critically damped. But since these interacting capacities are there, even though tau p1 is exactly same as tau p2, I'm not going to get critically damped, because this a1 r2, this particular term is going to make this tau 1 and tau 2 different. They are not going to same, even though tau p1 is same as tau p2. Please don't get confused. This tau p1 and tau 1 both are different. Tau p1 is the time constant obtained from the equation, which is nothing but a1 r1. a1 r1 is tau p1. Similarly, the tau p2 is a2 r2. So if I operate my system as a single capacity, in that case, I'm going to get the time constant tau p1. If I'm operating the system 2 as a single system, then I'm going to get the time constant tau p2. But if I arrange both these systems in an interacting manner, in that case, my time constant will not be tau p1 into tau p2. Instead of that, I am going to have the time constant as tau 1 and tau 2. Is it clear?
Yes,
Hello?
sir.
Okay. So inherently second order system, this gives the second order. So see, whenever we have the inertia associated with the system, it gives a second order differential equation, and therefore we get inherently second order system. Again, inherently second order system occurs rarely in chemical processes, and they are associated with the motion of the liquid masses or the mechanical translation of the solid parts. It occurs when the system possesses inertia to motion and resistance to motion and capacity to store mechanical energy. Okay, so we will stop here and we will continue from this point. We are going to derive the expression for the inherently second order system and also the first order system with the controller in the next class. Okay, we will stop here. Unless
Sir,
you have
we will-
any question, please go
Sir,
ahead.
we will cover higher order system also,
Yes. We will cover the higher order system also.
and it will be
In fact,
included in the minor syllabus.
whatever we cover before the minor, that will be the syllabus. So how many classes we are left with? 2 more classes before minor.
Yes,
Yes.
sir.
So we will have a class on Tuesday and Wednesday, isn't it?
G.
Correct?
Yes, sir. Yes, sir.
So we will try to complete a second order system, and if some lectures are available, at least one more tutorial I wanted to complete before you go for the examination. So maybe one more class we will cover the tutorial number 6. Tutorial number 6 we will try to cover. Okay, is that clear? In the regular class. So we stop here unless you have any other question.
Sir, how attendance will be marked?
So attendance is directly taken from the this website, this Teams. Teams can give you the attendance recorded directly. Okay, so that I will forward to the TA. Okay, is that? So attendance will be marked. Yes, Suchir, please go ahead.
No, I erased by mistake.
Not clear. What was the question?
No, I was telling that I raised the hand by mistake.
Acha, okay, all right. Thank you. So we stop here unless anybody is having any question. Otherwise, you can log off. Okay.